Delamination and peeling are among the most expensive and reputation-damaging failures in automotive coatings because they represent a complete loss of system integrity. Unlike appearance defects, these failures are structural, meaning the coating system can no longer protect the substrate or survive service conditions. From an OEM RD&I perspective, delamination is never treated as a paint problem alone. It is a failure of interfacial physics, stress management, and long-term durability design. Understanding whether a failure is adhesive or cohesive is the starting point for every serious investigation. Visually, delamination presents as sheets or flakes of coating lifting from the surface, often exposing the underlying layer cleanly. Peeling may initiate at edges, stone chips, weld seams, or sharp geometries, then propagate rapidly. The critical diagnostic step is examining where the failure occurred. If the coating detaches cleanly from the substrate or underlying layer, leaving that surface smooth and intact, the failure is adhesive. If the coating splits within itself, leaving material on both sides of the failure plane, the failure is cohesive. This distinction is not academic. It defines whether the root cause lies in surface preparation and bonding, or in film strength, flexibility, and stress tolerance. Adhesive failure indicates insufficient bonding between layers or to the substrate. Common causes include low surface energy, contamination, improper flash-off, missed recoat windows, or incompatible chemistries between layers. In many OEM cases, adhesive failure is linked to surfaces that looked visually perfect but were chemically inactive. Fully cured or oxidized surfaces resist solvent swelling and polymer interdiffusion, preventing proper bonding. Silicone residues, surfactant migration, oil mist, or even excessive flow additive accumulation can lower surface energy enough to cause adhesion loss without visible defects. Cohesive failure, on the other hand, indicates that bonding was stronger than the internal strength of the coating film. This is often caused by over-cross-linking, excessive brittleness, or internal stress buildup. High glass transition temperature systems, excessive bake severity, or improperly balanced resin-harder ratios can create films that are strong but unable to absorb mechanical or thermal stress. Under impact, thermal cycling, or humidity expansion, these films crack internally and peel even though adhesion to the substrate remains intact. Film build plays a critical role in both failure modes. Excessive thickness increases internal stress during solvent evaporation and cure shrinkage. Thick films also experience greater thermal expansion mismatch between layers, especially in multi-layer systems. Thin films may lack mechanical integrity, promoting cohesive tearing under stress. OEM plants tightly control DFT not only for appearance, but for stress balance across layers, particularly near edges and sharp contours where peeling initiates first. Solvent behavior during application strongly influences delamination risk. Trap solvents weaken interlayer cohesion and plasticize films unevenly. During service exposure, these solvents slowly migrate, creating voids or stress concentrations that trigger peeling. Conversely, aggressive solvents can overattack underlying layers, creating a weak, swollen interfacial zone that later collapses. Proper solvent balance ensures controlled swelling for adhesion without long-term structural damage. Bake profile and cure kinetics are often underestimated contributors. Rapid oven ramps can lock in stress before the coating has time to relax. Overbaking increases cross-link density, reducing flexibility and impact resistance. Underbaking leaves residual solvents and incomplete cure, compromising long-term strength. OEM RD&I teams validate bake windows not just for hardness and solvent resistance, but for stress relaxation and durability under cyclic loading. Environmental exposure accelerates both adhesive and cohesive failures. Moisture penetrates weak interfaces, reducing adhesion through hydrolysis or osmotic pressure. Temperature cycling amplifies expansion mismatch between substrate and coating. Stone impact creates microcracks that propagate along weak planes. Delamination often begins at these microfailures long before it becomes visible. This is why many failures appear suddenly in the field despite years of acceptable lab testing. Troubleshooting delamination requires forensic discipline. Tape tests alone are insufficient. They indicate only gross adhesion. Cross-section microscopy, fracture surface analysis, solvent rub tests, and environmental aging data must be correlated with process records. Identifying whether failure is adhesive or cohesive guides corrective action, surface preparation, flash-off, and contamination control for adhesive failures, formulation balance, bake tuning, and film build control for cohesive failures. The key takeaway is that delamination and peeling are system-level failures, not isolated paint defects. Appearance, gloss, and early test results cannot predict them reliably. Long-term success depends on managing surface energy, interlayer chemistry, internal stress, and environmental durability together. Once peeling begins, repair options are limited and costly. Prevention through disciplined process control and material understanding is the only sustainable solution. If you've dealt with peeling that made no sense based on lab results or early inspections, leave your questions in the comments. In the next episode, we'll move into stone chip resistance, explaining why harder coatings often fail faster, and how OEMs balance toughness, flexibility, and impact energy absorption in real vehicles.